Okay, I'm gonna show you some videos. Oh, wait, no, business. Lab, I forget, I'm sorry. 8, 9, yeah, this is the problem. Okay, we just finished 8. Yes. Okay. We just finished 8. Let's talk about that, and we'll talk about 9. Lab 8, how did it go? You guys all get it?
Hard.
Hard. So, help me, I'd love some feedback on this. So I think you're starting to see that neural nets are hard. Like you say they're hard. Probably the hard thing was not like sketching out the topology.
No.
Probably not even like crafting the loss function. It was probably something like just getting it to work. Right? Is that?
Yep.
Yeah. So I would love your feedback on this. Figuring out how to translate an idea, even an idea with very specific math, into functional PyTorch code is like a skill. Like, that is a hard thing to do. And debugging neural nets is not, it's not like debugging other code. Like your code is fine, but it's not working. Why isn't it working? I don't know. Like the compiler doesn't tell you. Like, is my learning rate wrong? Is there a bug? Was my computation graph messed up? Is my gradients matched? Are my gradients exploding? Right? There's a million things that can go wrong. So I don't want it to be, so I'm glad. I hope that you learned something as you tried to get this working. But I don't want it to be painful. Too painful. So talk to me. Let me know, how could this have been improved? I'd love to know your thoughts. Go ahead.
Something that was different about this one was Greg in the help session gave us kind of walked through a lot of the code of the training loop and kind of translated the math and the words into syntax. And that gave me a huge head start in the lab.
Okay.
And so that probably cut off 6 hours of time of me having to just kind of work through that in syntax.
Okay.
I really appreciated him doing that in the help session. You know, there were a few things, it wasn't perfect, but there are a few things we had to change, but for the most part, it was awesome.
Okay, good.
One thing that I did this time that I haven't done before was I was talking to Nick about his model, which was working a lot better than mine, after I submitted it. Because mine was working, it just wasn't working nearly as well. And his model was different than mine. It was a little more compact, and instead of using a resonant, he used a convolutional neural network. So it might help if we went over the best neural network after they've been turned down and went through and said, this is
what people did.
This is what the best submission was, and then pick it apart and see what we could do.
It's not a bad idea. Okay. Let's go here.
I would agree with that. There's major value in experiential learning, looking at someone else's successful example. I know that a lot of times in classes we shy away from that because we want to make sure that students are actually doing their work. But there's huge value in trying to do something and failing and then looking at someone's right example and saying what's different. I would love to see some of those things be part of labs, potentially, especially like this GAM lab. Mine didn't work out very well. It worked out enough to turn it in. I would love to look at some actual other implementations that I could actually run and compare and maybe try to improve mine as a result. Not feel quite so guilty about looking at other people's code, because in my job, that's what I do all the time. I look at other people's code, and that's how I learn, right?
That's how we learn.
And so I really like the idea of being able to somehow do that while still maintaining academic integrity.
Maybe after.
That's a little hard to understand, but I think that for this particular lab, it was really helpful to see some actual working code, but still have it so that I could, when I was like, I don't know.
Yeah, that's really interesting. I think we could kind of rejigger the way we do the labs. You've got me thinking now. I'm wondering. Sometimes, my daughter in high school does this, where she'll take a test, and then the professor will say, for anything you got wrong, you can go back, look up the answer, write a little thing about why you got it wrong, and resubmit your test, and it gets regraded. I'm that's way too much work for me. But maybe what I could do is something like it's due on Saturday, I give you some working example on Monday, and you can go back and revise your submission and compare what you did with a working example and get your example working just like a day later. Or like I don't know, I'm wondering if, yeah, there's some way we could do that.
Yeah.
I'd love your thoughts on this. This is good. Okay, good.
I was thinking, along those lines, maybe what you could do, I don't know if learning to allow this because it's learning to, but maybe after you submit an assignment, you can now see something that is
Right.
the solution. You can like, once you've actually done something yourself, whether it's good or not, you can then go see.
Right.
Also, I really liked there was that, I can't remember what it was exactly, but it had like the research paper and then like a code block and then like a chunk of the research paper and like the code block. I don't remember, one of our labs had that.
Yeah, annotated notebook, yeah.
Like if there was just a small, like the most pertinent parts of the research paper, like I know we talked about them in class, but if it was possible to just have like in the specs, like a chunk of the research paper and then not code, just like a reminder of like what it did, you know what I mean? Like for instance, just like the part that had the math, and like that part, like once the TAs reminded me in English like what that part did, it was like, oh, that's so obvious how to code that. But before that, I was like, what? They're all like the squiggles and doubles and stuff.
Okay.
So like just like the key parts, like without giving the code, just like another like plain English, like a paragraph of that would be really nice.
Okay, so. Good.
I personally like this lab a lot. This one I answered the question because we got to build it from scratch, and I think that really helped me like understand what's going on with like the LSTM lab. I don't really understand what's going on, and I'm just reading what they're saying. So I think it'd be good if we can like just build our own thing and then see a solution and then see if anything's going wrong. But I like building from scratch.
Okay, good. Go back here.
So I think with a lot of the labs, you can get a result. And since we're not great on accuracy, that result like might be okay. But since we don't have the time to go in and actually get like decent results, we don't actually like go through all the mechanics of the little details that we're setting up. And then you get to a lab, maybe like this one, where those little details that might have been the only way to get it to work. And with previous labs, and I know you want to fit a lot of different applications, like one lab every week, but I took over the summer 601, so Pharaoh. So we did, it was similar, we did similar stuff. It wasn't all deep learning, but there were less labs, and we were graded on accuracy, so we had to actually get it working well. So I felt like I learned like a lot of like the nitty-gritty details that you kind of needed to learn in over like 2 or 3 weeks, and so that helped later on. Whereas maybe with some of like the first labs, you didn't need to actually learn all that stuff because you could kind of get it working, even though everything looked like in this one. If you didn't get the gradient penalty working, I think you could still get something, right? And so I think you can have stuff that doesn't work, and it still gives you some results. But since we're not going to do an accuracy, it doesn't always.
Okay. Okay.
So I actually think part of the challenge here is that this class isn't an isolated class, right? It's actually the 3rd machine learning class I've taken in the department, and I know there's some others like you was talking about that I've not taken. And it almost feels like the faculty, and no offense, but it almost feels like the faculty are not coordinating what's being taught in all the machine learning classes and what tooling is going to be used in each of those classes. Because in every single one of those classes I've taken, it's a completely different tooling set, it's a completely different approach to machine learning, and how much we're cracking the model open versus how much we're trying to gain an intuition about the model, like which models are good for which sort of problems. It almost feels like this is not a problem that you're going to be able to fix in one class, but over the course of 3 or 4 different classes, you can get a more holistic view of machine learning to teach both the intuition and the math underneath it.
Yeah, the problem is none of our machine learning courses are prereqs for each other.
Yeah.
Which you're right. It feels like we don't coordinate.
And I'm sure
That's because it's true.
But that's been my biggest frustration, I think.
Well,
It feels
yeah.
like they reset on every semester, and so I still don't feel like I have really good intuition.
I think this is why we need a data science major. Yeah, but Okay, we gotta hurry quickly. So Colby and then we're gonna go.
Yeah, sure, really quick. I was just gonna reiterate what he said. Basically, I was able to get like a working model-ish,
Yeah.
but like I feel like I could have taken like a whole nother week and done like a whole like second lab just like refining and making it actually have like good looking images and stuff.
Okay.
And so and I feel like that's almost like the more value, maybe not the more valuable, like the next most valuable thing that that I need to be able to learn is like how to actually make the results like better and stuff.
Okay.
So far in the labs, I don't know if I've had that chance, just because it's been good enough to turn into something that's like working.
Okay, good. Here, then we gotta be done. Go ahead.
Just a feedback about Colab.
Yeah.
I don't know if other people started running it locally or not, but Colab doesn't save things and it only runs so long. So when you get a lab, so it wasn't that big a deal for the other lab. When you get a lab where you want to train for like multiple hours, or maybe you want to train it overnight, you have to do a lot of like trying to save and then download and stuff automatically. And it was kind of a pain for labs where you have to train for a long time. And so, I don't know, that's kind of, I think the biggest downside of Colab is that there's no persistent memory. That was tricky.
Okay.
Honestly, not to oppose like what's been said about like coordination between classes, but I actually really like the fact that, you know, the tool sets aren't the same, because in the end, like coding isn't the tool set. Like in the real world, we're gonna have to change. Like I was really familiar with TensorFlow and Keras before I did this class, and I'm glad now that I know another tool set. And then also with like prereqs you mentioned, like adding prereqs that's what I really don't like about computer science. Is like you don't need to know how to do an Android app if you want to learn about deep learning. You know, it's like a completely different thing. And I've liked that I got in this class without doing like a lot of the prereqs that other people have done. I've done any of the machine learning classes, but I've learned a lot on my own. And coming to this class, I feel like I've been able to understand because of that. And like when you start making all these formal requirements, we're going to do it this way, and overdoing it, then I mean, really, it takes away from I think your ability to like self-learn and stuff. And even with these labs, like even after I turned them in, like I turned my lab in last week, and now I'm training a new GAN because you know I feel like I can do better, and just because you know the lab's over or whatever doesn't mean you can't continue to learn and things
That's
like that.
right. Just
And I
because
feel
the
like the
lab's
grading's
over.
been pretty generous. Like the grading on the actual output of the pictures was pretty low. So like even if you didn't get great results, you'd still get named in the class, and now I'm still continuing to improve my model.
Good. Okay, thank you for this discussion. This has been very helpful for me. I would like to give you some good reference code. So I think what I'm going to do is find some of the people who've got the best results and see if they'd be willing to share their code with the class, and we'll send it out to you. And then you can just see, compare how they did it. Okay, so speaking of labs, so let's talk about the next lab. So I was really wrestling with the next lab. I really wanted you to do a reversible network, but I realized two things. Number one, I think it would be useful, but I just don't think we have time. Because as I looked at the schedule, I was realizing I really wanted to have you do a deep reinforcement learning lab. And that's the next one after this one. And so I realized, and I want you to have more time, not less, to do that. Because of all the labs, like, you're gonna love this. If you thought getting GANs to work was hard. So I think we found that DeepRL, like, it's magic when it works. It is so cool. Like nothing thrills me quite as much as seeing one of these little reinforcement learning agents play video games. But it's tricky, like, and you have to get the details right. And so I want you to have time to work through those details. So so I decided to go ahead and cancel this week's lab. So that'll give you 2 weeks for the DeepRL lab. If you're super offended about that, let me know. Okay, so let me tell you about DeepRL. So yeah.
Do you know where
The new lab spec is. So I want it to be doable for you, and so the lab spec will almost certainly be implement the DeepQ network. DeepQ, and not like that's it. So what we talk about today, you should be able to just get going. So there's no spec up, but we were going to try to get that up as soon as we can.
Thanks.
I know I've said that before. Okay. Okay, so let's talk a little bit about, I want to just show you a little bit about where we're going. So deep reinforcement learning is a little bit different. So we're like switching gears, okay? So mentally, like, I don't know, Do a little palate cleanse, a little amuse-bouche, something. We've done supervised learning, we've done unsupervised learning, and now we're going to do reinforcement learning. So how many of you have ever heard about reinforcement learning before? Most of you, okay. So, but some of you haven't. So you know that reinforcement learning sits somewhere in between unsupervised and supervised learning. In supervised learning, we have inputs and outputs. In unsupervised learning, we only have inputs, or just piles of data. Reinforcement learning is in the middle. So in reinforcement learning, we think about agents and environments, the actions those agents take, and the rewards that they get. And agents have to both learn about their environment and plan to act in that environment at the same time. So some learning means planning. And the reward signal that they get is not the same as supervision. So for example, if I'm a robot and my job is to, I don't know, maybe I'm a household butler robot, and my job is to unload your dishwasher, and I start unloading the dishwasher, and I do my best, maybe my owner would say, hey, that's pretty good, I'll give you 2 cookies for that. And the robot's like, is that good? Like, have I gotten more? Is that the optimal number of cookies I could have gotten? So there's no, it's not like the person didn't tell you what specific mistakes you made or what specific things you did well. You just get some sort of aggregate reward signal. And it's the agent's job to untangle everything. Okay, this is a very abstract framework. So I want to show you a few little videos just to make things a little more concrete. Here's a little control problem that was solved using reinforcement learning. It's called the pendulum problem. And you have a little cart on this track, you can move back and forth, and the goal is to swing the pendulum up to the top and then balance it. So this problem was solved using something called deep reinforcement learning. This is an agent who's you're trying to get it to learn how to walk. It's a 2D planar robot. Here's a little spider version of the same thing. You're trying to get it to sort of crawl, I guess. So here the rewards are things like forward movement, and the environment is whatever information the agent has about its environment. So things like angles of the joints, where you are relative to the ground, angular velocities, whether or not you've made contact. So this one, the robot is attempting to move its end effector, grab that little ball and move it to the red target point. Okay? And importantly, in this one it's just looking at the pixels. So this is like its input, it sees this as its state space. It doesn't see joint angles directly. Here's the more fancy version of that with cool graphics. So the inputs or the state of the system is whatever information the agent has. There's some reward, which in this case it's called episodic, so you get a reward if you manage to get the target to where it's supposed to be, and you get no reward otherwise. Like I said, this is abstract, and so while we can think of things like agents, we can also think about things like, let's see. So this is a car driving one. So here, you feed the neural net pixels representing what the car sees, and the car has to decide what actions to take. So which angle should I steer at? Should I brake? Should I accelerate? And then you get reward based on whether or not you crash, based on whether or not you make it around the track, things like that. Okay, but you can imagine more, like I said, more abstract versions of this. So you can imagine framing reinforcement learning as a conversation. So maybe an agent talking to another agent. You can imagine that the state space is the history of the things that have been said. The reward is whether or not the person seems engaged. You can also imagine games like chess, checkers, or Go. And so how many of you have heard of AlphaGo? Most of you. Have you seen the movie? A couple of you? Have you seen the trailer? I forgot what's the trailer. This is a couple of years ago. If you haven't seen the movie, I've got it on my laptop. They let me download it. The guy who did this is one of my good friends. His name is David Silver. We knew each other back at MIT. And he was like the lead guy on this. And they gave me a copy of the movie, so anytime we can screen it anytime we want. So I just wanted to show you this because I'll tell you some funny stories about this. But I think it's interesting. Well, what I want you to watch for as you watch this trailer. So this movie is about a deep reinforcement learning agent that solved the problem of Go. So it beat humans in Go. What I want you to watch for is the cultural impact of this.
It's the world's oldest continuously played board game. It is one of the simplest and also most abstract.
beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge. The whole world is watching. Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
This is developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think something went wrong.
Yes, maybe.
He's got to be a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
It's on Netflix. Okay. So I think that's, I don't know, when I watched that, I'm like, I never would have thought he could make, it feels almost like a James Bond movie or something like that. It feels super intense, and there's like all this music, and I'm learning, I don't know, we're pretty mild guys here. So my friend Dave told me a story. He says, so AlphaGo, like it was pretty big news in the United States, but it did not make the same splash in the Western Hemisphere that it did in the Eastern Hemisphere. So Go is a lot bigger deal in Asia, and he said there it was culture. It was this cultural earthquake when AlphaGo defeated Lee Sedol, and spoiler alert. So it was this really it was this momentous occasion. He said, in fact. He said he gave a couple talks out there. It was like stadiums full of people. They were interested in this. And he said in Korea, they coined a new word, which was to AlphaGo something. And so to AlphaGo something means like you blow it out of the water, right? Oh, you totally AlphaGo'd that. And I was like, wow. So it's really impressive to me to see kind of how much cultural impact some deep reinforcement learning stuff had. So, anyway, if you haven't watched the movie, you should totally check it out. It's a lot of fun. So I showed it to my kids, and they loved it. It's not very technical. It's really fun, and after they watched it, they're like, okay, we're in. We all want Go boards for Christmas.
Okay. You weren't supposed to learn deep learning.
Yeah, it's a lot of fun. So. Let me know if you want to screen it. We can set up a time to screen it, maybe as a class sometime.
4 o'clock.
Okay, but today we're going to start learning about DeepRL. We're going to spend a bunch of time on this. So for about the next 2 weeks, we're going to learn about DeepRL. So I was preparing some lectures on this, but I decided actually David had put together a fantastic tutorial, and I thought we should. There's no reason for me to recreate these slides, so we're going to use his slides. I want to take you through. The basics of reinforcement learning, and then we'll go through where deep learning enters into reinforcement learning. Okay. All right, stand by. Okay. So reinforcement learning, like I said, learning meets planning. By the way, in Go, so the state space is the configuration of the board. That's the inputs. And the reward, what do you think the reward is?
When you're winning.
That's just like win or lose. So there's another important dimension of reinforcement learning that I think is illustrated well with the case of Go and other games like it, which is sometimes the reward is disconnected from the specific actions that led to that reward. So in reinforcement learning, if you win the game, you get 1 cookie. If you lose the game, you get -1 cookies. And nobody tells you which move along the way was good and which one was bad. It's up to you to figure that out. Okay, so that's called the temporal credit assignment problem. So you have to figure out which of all your actions led to the rewards that you experienced. Okay, so we have an agent, we have some actions. So in the case of Go, the agent is the thing playing. The actions are which pieces you put where on the board. The reward is whether or not you win or lose. If you're a robot, the actions are what voltages do I send to my motors. The inputs or observations are what does my potentiometers and my accelerometers and my rotary encoders tell me about my joint angle space. And my reward is something like, am I moving forward, or some other measure of a task. And the goal is to somehow pick the actions. So inputs come in, you read in like whatever it is, you read in your joint angles, you read in your board state, and the neural net's job is to spit out some actions. Okay, so we're going to map inputs to actions. And the question is, how do you train the neural net to do that? I think we can all imagine topologies. The question is, how do we set up the learning problem? And so we're going to use the mathematical framework of reinforcement learning to help us understand what the loss function and what the inputs and outputs all need to look like. And we'll see it's a little subtle. It's not probably what you would have come up with. So, okay, so we've actually seen a lot of this stuff, so we're going to skip a bunch of his slides. Okay, so reinforcement learning is actually a very generic kind of thing. It has contact with many different fields of science, including operations research. There's a bunch of neuroscience that goes into this. This is where dopamine comes in. So it turns out that your brain, at least at some of the lowest levels, runs something that looks like a classic reinforcement learning algorithm called temporal difference learning. And dopamine is essentially the reward signal that that algorithm feeds off of. It's kind of cool. But it turns out that there's all sorts of reinforcement learning that contacts all sorts of areas. We're just going to focus on kind of the most abstract, and we're going to do the deep version of it. Okay, so just some like terminology. So agents acting in environments. So the things we care about are actions, handily denoted A, subscripted by T, so time. So at every time step, the agent spits out an action. They receive some observation and a reward, could be 0. And the environment, so there's like some agent here, the environment, you give it an action and it gives you back the reward and the observation. And then there's some state which the environment keeps track of. So, and as you interact with it, it updates state. You may or may not be able to observe that state. So when we talk about experience, or the experience that an agent has, it's just a sequence of these things. So you get some initial observation and reward, you take an initial action, and you get your next observation and reward, you take your next action, and you just keep doing that. So it looks like this stream of triplets. Observation, action, reward, observation, action, reward. You get this whole stream. And the state of the system, so this is the formal definition of state. So state is a summary of history. And in the case of a fully observed environment, that is equivalent to the most recent observation. In other words, the observation tells you everything that you need to know about the system, and you can forget about the entire past. This is called if a system satisfies this property, it's called fully observable. So an example might be the following. Let's suppose I want to build a missile tracker, and suppose I want to build some sort of missile tracker, and my observations are things like radar images, and the true state of the missile is like some coordinate in space. If you imagine that the missile does something like this, it ends up here at time t. So this is the state at time t. Now let's suppose I somehow magically measure that directly. I have another missile that does this, that ends up in the same location. That as far as predicting future possibilities of where it's going to be, the history doesn't matter. Knowing that it was here at time t, I know everything I need to know about the missile. So I can forget about the past. We'll see. So is Go, so let me ask you this, is Go fully observed or is Go partially observed?
Fully observed.
Fully observed, because the board game state, like, that's it. That's all there is to know. And you can forget about how you got into that particular position. The only important part, as far as deciding what to do next, is tracking that state. Yeah.
wouldn't that prevent it from being able to perhaps maybe learn something about the current opponents, like tendencies or
Okay.
strategies?
Yes, so good. So the question is, wait a second, if we're just talking about the game state, but of course, how we got to a game state is relevant if we're doing opponent modeling. We'd like something, how we got to a particular game state might tell us about how they're thinking, and then we can maybe take advantage of that if we can somehow model it. Yes, and in that case, if that is true, then we have to draw the box bigger, and it includes the mental state of the person in addition to the board state. And that's our complete state, and we only observe part of it. In which case, history matters, and this is no longer true. Yeah. Good, okay, yeah.
So earlier you said that the reward that the network is given is basically whether or not they win the game.
Yes.
But here it seems like it's getting a reward after every move it makes. Is that the
Yeah,
case?
so it can be 0, 0, 0, 0, 0, 0, 0, and then at the very end you get something plus everything.
Okay.
Okay? Okay, so a couple of auxiliary objects that we sometimes talk about in reinforcement learning. So there's the policy. Policy is something that determines how an agent is going to behave. It's typically a mapping from states to actions. So in this state, I do this. In this state, I do this. We'll talk about different ways to represent policies and different ways to learn policies. A value function is a measure of how good any particular state is. So for example, in the game of Go, you can imagine that the value of being in a winning state is very high, and the value of being in a losing state is very low. And then there's values of all the states in between. And if we knew the values of all of the states, that would be super helpful to know. So really good chess players and Go players have a mental model of, as we're moving and we get into some board configuration, like, oh yeah, this is like a really good configuration. You might not even be able to articulate why. Just like, yeah, history has taught us that this is a really strong position or something. Okay, so let's call the value function. We'll talk about that a little bit more formally. And then a model is something that an agent may or may not have, and it's a representation of how the environment works, which can be used for things like planning and acting. Okay, so there's two different kinds of policies, deterministic and stochastic. Deterministic is exactly what it sounds like. You give me a state, I give you an action, and there's some function that just like computes that. Could be very simple, like a lookup. If you have a discrete, finite number of states, like let's say you're in a little maze, a policy would just be a mapping from any particular XY coordinate in the maze to a direction that you're supposed to go. And you can just look that up in some data structure. Much more complicated value policies, however, we'll talk about things like the Go example is a good one because, as they said, there's more board configurations than atoms in the universe. So there's no way we can enumerate all of them, even though it is a discrete number. And it's even finite. But it's too big. So we have to approximate that function. Stochastic policy is similar, except as it applies, you give me a state, I give you some distribution of actions, which you can then sample. Okay, so let's talk a little bit about value functions. So value functions are one of the keys to reinforcement learning. So the idea of a value function is some mathematically precise representation of how good it is to be in a particular state. And we formalize that idea by saying that the value of a state is how much is like a prediction of how much future reward you might be able to get from being in a state. And in particular, it is the expected discounted reward of being in a state if you follow a particular policy. And this is a little bit subtle. So let's talk a little bit about what this means. So first of all, a value function is not the same as an immediate reward. Okay? An immediate reward just tells you how much reward you get for being in a state and doing a particular action. But a value tells you something about all possible future rewards. So that's good, because that means that a value function, let me ask you this. I'm going to show you a very simple world. It has 5 states. So there's a start state and 2 actions, which will take you up to state 1 and state 2. And then from here, there's only one action that takes you into state 3, and then it just takes it back to itself, and it gives you +1 reward. And here there's only one action, and it takes you into state 4. And there's only one reward, and it gives you -1. Okay. So, what is the reward? The immediate reward for being in state 3? +1. What is the immediate reward for being in state 1? 0. What is the immediate reward for being in the start state? 0. 0 minus 1. Okay? What is the value of being in state 1? Right, something like positive, right? This is good. Would you rather be in state 1 or state 2? State 1. And if you are in the start state, what is the value of taking action 1 versus the value of taking action 2? I don't know, but like this one's higher than that. Okay, so that's the difference between value and reward. Now, let's make this just a little bit more complicated. So what if we had action 1 here and action 2 here? And what happens if we get -1 reward here and +1 reward here? So now what's the reward for taking action 1 in the start state? -1. So do you want to take action 1 in the start state, or do you want to take action 2 in the start state? You still want to choose action 1, right? Because sure, there's like a little bit of pain at the beginning, but then, oh my goodness, you reach nirvana. And you're like super happy for infinity, and it's great. So you'd rather have an infinite number of 1s, even if it costs you -1 here. Okay? The chess version of this might be something like a queen sacrifice. Okay, you're in some state, and like there's this super painful thing that you can do, like sacrifice your queen. But if it takes you to a place where you can checkmate your opponent, then it's worth it. And so value captures that idea. So the value of taking action 1, very, very good, even though the immediate consequences might be negative. Value of action 2, very, very bad, even though if you took the greedy action, it would look good. Okay, so the value function is how much reward can you get from being in a particular state or a particular state action pair. If we think about state action pairs, that's called a Q value. So a Q value, you give me a state and an action and a policy, and I tell you the expected value of future rewards. So I sum them up. Now, you see this little lambda thing here. That's called a discount factor. The discount factor tells you, it discounts future rewards geometrically. So at every time step in the future, gamma is raised to another power. So gamma is typically between 0 and 1. And so what effect does this have?
It rewards current action.
Yeah, so it sort of weights proximal rewards more than distal rewards. By the way, people do this all the time. There's all sorts of psychology research about human decision making, and we way value $50 today more than $100 a year from now. It has nothing to do with inflation. It's just like, it's like that's just the way our utilities work. And we'll see that this has some nice mathematical consequences. But so what that means is, by the way, this also lets us, it turns out that even though the sum of a bunch of rewards might not be finite, the discounted sum will always be finite. So for example, let's look at this little MDP here. Let me ask you this. Suppose this is +1 and this is +2. If we say that the value of being in a state is the expected sum, t equals whatever, to infinity, of the rewarded time t, what's the value of taking action 1? Infinity. What's the value of taking action 2? Infinity. So which one's better? Okay, like intuitively we think that action 2 is somehow better. But this definition doesn't quite get us that. If we stick a gamma here, gamma to the t, and let's say gamma is some number like 0.9. Now, what is the value of taking action 1? It turns out you can solve this, and if this is our reward, if the rewarded time t is always +1, then it's just RT over 1 minus gamma. And so what is the value of taking action 1? 10. What's the value of taking action 2? 20. Okay? So by geometrically discounting future rewards, it turns out that this infinite sum, which would otherwise be unbounded, becomes bounded. All right, and this lets us distinguish these two cases. Interestingly enough, and this is the key to deep reinforcement learning, value functions obey what's called the Bellman equation, or there's a particular recurrence relation. So let's look at the definition here of a value function. So notice that Q value is the expected sum of discounted future rewards. But if we look here at this, imagine that we just kind of look at the RT plus 2 bit and put some like parentheses around this out to infinity and factor out a gamma. Then you get gamma times a reward plus gamma times a reward plus gamma squared times a reward. And that is exactly the definition of the Q value of whatever state you ended up with at your next time step.